The beauty of iron is that ordinary people really don't think about it at all, okay? But it completely changes the quality of life. So, for example, when I was a child, we used to collect food to send to regions where there was starvation on an unbelievable scale. You're not talking about hundreds of thousands, but millions of people actually dying because of a lack of food. That changed completely when mechanized farming started in the US, okay, when mass production of food, which spread throughout the world actually, became possible, entirely reliant on steel. Okay? The massive machines that we use are made from steel, and we can now feed a population of 8.5 billion people without any problems, except in conflict regions where starvation still happens, but nowhere near the scale that used to happen. So I'm going to start by explaining to you why iron is even more important than you ever imagined. So there was a professor in Cambridge called Fred Hoyle, and he is the one who coined the phrase Big Bang, or the origin of the universe. And he, along with some other people here in the US, created the theory to calculate the abundance of elements in the universe. And the theory is actually a very long paper, which I'm going to summarize in a few seconds. So this gives you the stability of the elements versus atomic number. And initially, we had hydrogen, and then hydrogen atoms fuse to form helium. And some of the mass is lost in the process, so you get a huge amount of energy released. And that sort of fusion can continue until iron, because iron is the most stable element in the universe. After iron, if you try to fuse elements, you don't actually gain energy. You gain energy if you split them up towards iron. So these elements are accidental. They are metastable. They should not be there, but they form in dying stars when they explode. So they are metastable elements created in dying stars. And eventually, they would end up at iron. And there is a statement in this paper that if you're not working on iron, you're really in trouble, because eventually the galaxy itself will completely transmute into iron. So it's fascinating, actually. Iron features in every subject, not just in the sciences, but also in the humanities. Now, there is another really important feature about iron, and that is that it has an iron atom has an electronic structure, which is the same as that of argon, plus some extra electrons thrown in. And the exclusion principle says that in each energy state, you would put one electron first, and then put another one of opposite spin. So these are, if you like, the lonely electrons, which don't have another one of opposite spin to pair with. And this is what gives iron the magnetism, because I want you to imagine that an electron is spinning around an axis. The spin axis are arrows over there. So it shows you the current going around an axis, and that will have a magnetic moment. And this is why iron is ferromagnetic. But it's much more than that. Why should we worry about whether it's ferromagnetic or not? Well, if you do first principles calculations, and this is a colleague of mine, Tony Paxton, who did these calculations, even if these forms of iron don't exist at all, you can work out their energy as a function of density. So you can make iron in the diamond structure. But the energy is so high that it's very unlikely we can ever actually make it in practice. But using first principles calculations and ignoring magnetism tells you that the stable form of iron should be hexagonal close-packed like this, not the body-centered cubic structure. That would have a profound implication, because hexagonal materials in general are not as good as cubic metals. So in the absence of ferromagnetism, we would not have civilization as we know it now, because we would not have the body-centered cubic form of iron, which is the majority of the 2.5 billion tons of steel that you consume every year. So you have to thank ferromagnetism and tell all your friends that, look, I'm now going to switch to a very topical incident that happened in the very busy shipping lanes next to the coast of Britain and in between the coast of Britain and France. So there was a tanker here, anchored, so completely stationary. And a container ship went and crashed into it. It's still under investigation. You know, the Marine Investigation Branch is looking into the details, but a very severe crash. And the tanker was carrying fuel for military aircraft. So immediately you had this huge impact. It caught fire. And tragically, one person is missing, presumed dead from this. But I want to show you why this incident is not as severe as it could have been, with only one life lost. And probably that life was lost because of the fire rather than the collision. This is an incredible story which illuminates why steel is so important. So the container ship is called the Solong, and it was made in the Netherlands under a Portuguese flag, right? I don't exactly know what that means, but I suppose the legal entity that owns that is Portugal. And the Stena Immaculate was designed and owned by Stena in Europe. It was built in China and hired by the US military, I suppose, to transport the fuel. This is the huge gash caused in the Stena Immaculate. I mean, just look at it, all right? The scale of it is like meters of damage on that ship. So I'm going to go through a very short calculation to show you what this means. So feast your eyes on this. So the rough calculation is, I know from the Marine Investigation Branch's initial report that the Solong was moving at the speed. I've converted to meters per second, but it's about 16 knots. Actually, you know, the shipping companies use really weird units. So for example, if they talk about the gross weight, it's actually the volume of the ship they're talking about, not the mass. So I had to do quite a lot of research to actually find the weight of the ship, and it's about 8 million kilograms. So you got 8 million kilograms moving at 8 meters per second. What is the kinetic energy? Well, you know, I'm sure you know this, but it's half mv squared, right? So that is 30 million joules, huge amount of kinetic energy. And I've used the dead weight of the ship. And that might exclude the weight of the ship, but I cannot find that information, okay? So the weight could actually be bigger than this. Everything tells me that the dead weight is the weight you carry, not the weight of the ship. So anyway, let's assume a conservative 30 million joules of energy. Normal ship steel absorbs the stress it can support multiplied by the plastic strain. It can absorb that much energy, right? And that is why you travel in cars which are made, even the fancy cars will have steel because you need safety. And you know, horrendous head-on crashes, people walk out of the passenger compartment because of the absorption of energy. So the deformation would have absorbed 90 million joules per cubic meter, right? And I converted the cubic meters into an area. So we need about that much volume of steel to absorb the impact of the Solong ship. And hull steel is 12 times 2 millimeters thick. I'll explain the term 2 later. So there should be a 9-meter gash produced on the tanker, and that's about right. To come up with a back of the envelope calculation that this is the size of gash you would produce with the steel absorbing the impact of the Solong container ship. As neither of the ships sank, and they are both now have been towed into UK port facilities for salvage, for investigation first and for salvage operations later. There is no other material, not aluminum, okay, or any other material which could have achieved this. not a single material. That is why we use it as a safe engineering material. So if some uneducated person tells you that graphene is 200 times stronger than steel, actually it is not, all right? And furthermore, it doesn't have a metallic bond, which means that when you break it, you break it. There's no plastic energy absorbed. And many years ago, the same story happened with carbon nanotubes. And I wrote a paper and I sent it to NASA, who was sponsoring a project to make a very big rope into space, a Russian idea, so that you can climb into space rather than a rocket. And I explained using thermodynamics that this is impossible to scale from a minute size to anything greater than 2 millimeters. And you no longer hear about space elevators. So there is another reason why the disaster was not big, because when you have fuel spilling, you get pollution and so forth. But the engineering is so brilliant. So this is before the crash, and there are 18 separate tanks in here. And depending on who you believe, either one or two of those tanks were ruptured, but not the others. So the amount of fuel spillage was actually very small, and there are no reports of seabirds, etc., being harmed by this. And furthermore, it is double-hulled. That means, if you look carefully at that picture that I showed of the gash, you've got 2 layers of steel to penetrate through, right? And that is a regulation for any fuel transporting ship in territorial waters. It must have a double hull. Now, the disadvantage of that, of course, is that you are using more steel, and that's not a good thing. We are producing a lot of CO2 by consuming so much steel. So I'm now going to show you the latest technology. We started in 2014. That this is the normal, the dashed line is the normal ship steel, the normal ship steel. So this is the conventional ship steel used in the vast majority of ships. And one of my former PhD students who now works at Nippon Steel, so Kazutoshi Chikawa and his team, produced another ship steel, which is much more ductile, same levels of strength and so forth. But I was talking to a member of staff earlier, and we had a really nice conversation where we decided that it doesn't make sense to just talk about one property when you're talking about making something. You have to have a bank of properties that are important. Strength, of course, is important. And I need to explain to you what the meaning of a Pascal is. So if you take an apple, the weight is about a Newton. A Newton is a force. So the weight of an apple is about a Newton. And if you put it on 1 square meter, that's a Pascal. So a strength of 400 megapascals means you can support the weight of 400 million apples on 1 square meter. That is incredibly strong, all right? But in the context of steels, that's not particularly strong. But to an ordinary person, they would be very impressed if you explained what a Pascal means in this way. Very important that you must be able to join the pieces of steel. And you created a nice steel with a beautiful microstructure, and then you more or less destroy it by putting a localized heat source. So it has to be tolerant to welding. And that is really a huge, huge challenge to do, is to make the right properties plus join it. And there are many other things, and toughness is one. That means, when you hit it, it's got to be able to absorb energy because that's what makes it a safe engineering material. And you've got to be able to mass produce it in the right form, okay? like in this case, plates, which are about 12 millimeters thick. So with this new technology at Nippon Steel, we now, and of course, this is another very important thing, which everybody who's had experience in industry will know, that you can't actually market something that is safety critical without satisfying all the insurance and certification authorities, including governments. So that's not a straightforward procedure. You have to have that before a company will even make a ship which can use your new material. Okay, so we have all that. And if you look at these micrographs, optical micrographs, you've got the ordinary steel and the new steel. They don't look all that different, right? Yeah. To the untrained eye, these don't look all that different, but this is the new steel, all right? And these dark patches here, they are often known as pearlite because, if you look at them from different angles, they will look like the iridescence of a pearl. So it would look something like this in a cross section, but actually that's not correct. Oh. Yeah. So imagine, so a colony of pearlite is a bicrystal interpenetrating two crystals of cementite and ferrite. So if you think of a cabbage as the cementite, all the leaves are connected, so it's a single crystal. And then you put it into a bucket of water. The water is the ferrite. So you can see how intimate that mixture of cementite and ferrite is in 3 dimensions. It's only when you slice the cabbage and look at it in a narrow region that you think it's alternating plates of cementite and ferrite. So in the new steel, these dark regions are not simply pearlite, but you have these structures here, which make it a little bit more homogeneous. So when you're pulling a tensile specimen, if you've got one region deforming a great deal more than the other, then you will get fracture earlier. So very subtle modification leads to a steel which you can have a single hull. And many mineral carrying ships are now made using a single hull and saving quite a lot of steel in the process. So I'm going to show you the massive experiments that you need to do to prove this to the certification authorities and so forth. So here you have got a steel sample which is clamped, and this is a huge sort of, I don't know what to call it, but it will push into, it will push into the steel. And this is the old technology, and you will see at the top that the steel fractures. Yeah, you could, saw that huge crack developing, and that's where the water would come in or the oil would go out if you're single-hulled. Now, this is the new steel. It's called unsafe hull, and the same experiment, and there will be no fracture that you see. Same experiment, and the steel remains intact, and I can show you, the images of the steel after the experiment. This is the old and the new. It establishes that you can make ships, and there are many ships now made using a single-hulled ship, although the regulations for transporting fuel still require a double hull, but that might change over time. This is now the world's first adoption of this new steel, and it started in 2014. Nippon Steel, Sumitomo Metal, and the shipbuilding companies have collaborated to make this come to life. Yeah. So I want to put it on your phone. My point in using this story is that it is topical, right? So you will all have heard about it. But you will not have heard about the miracle, that caused only one loss of life and the lack of pollution from the result. No ship sinking, right? They're both now in a harbor in Britain. So, what you guys do in material science and engineering, people don't know about your achievements, and you've got to talk about them a lot more. So this lecture is being recorded, and we hope to put it onto YouTube afterwards. Right, changing the story again. I was writing a book, and I wanted to use this image of crystals of almost pure iron, which were brought back from the moon by the Apollo missions. And they look beautiful. I was not comfortable with using these images because I don't understand why you would get a crystal with 5 faces here. Can you see a 5-sided face? So 5 sides is not consistent with long-range symmetry. So it bothered me, and I don't want to use a picture which I don't understand. So I tried very hard to solve this problem, and was not getting anywhere fast. So what do you do when you fail? Phone a friend, yeah? So I did that. Now, just to explain what a crystal means in normal life. So Lawrence Bragg in Cambridge derived and his son derived the Bragg law, which allows you to probe crystals and to decide on what arrangement the atoms are in. But nowadays you can even see the atoms. So this is a picture where every single dot represents an atom. So you can see by having a huge magnification in an instrument called the field ion microscope, the actual arrangement of atoms. But the definition, the conventional definition of a crystal is that it has long-range periodicity. You only need to have a handful of atoms, the arrangement of a handful of atoms, and if you repeat that, you generate the entire structure. So here, for example, is a cubic structure. And if you look at particular planes on this, so this cube plane, for example, we label that as 100. Don't worry about the labeling, but small numbers here mean that it's a nice, neat face, 100. And crystals like to have nice, neat faces. So these are, for example, crystals of iron sulfide, which are cubic in crystal structure, and they have nice cube faces. Of course, they can have other faces, but if you give them a chance to evolve, that means time and temperature and so forth, they will adopt a beautiful shape. And ordinary people regard crystals as something having a beautiful shape, but they don't have to. We can make turbine blades in jet aircraft, which are single crystals, but in the form of an aerodynamic shape. So just remember, this is a simple face, and therefore the indices are very simple. So I got Kevin Knowles here, is the friend I phoned, and he's very meticulous. And he spent 3 months on this problem. So these are pure iron crystals brought back from the moon, Apollo 15 mission, and about 3 micrometers in size, and they grow from the vapor inside cavities in the rock. So they are isolated from water. So, the Earth, 4.5 billion years ago, had elemental iron, and iron dissolved in the oceans. There was no oxygen, plenty of methane. So the temperature was so high that there was no rain. So you had elemental metals on the surface. And it's only when certain creatures in the ocean started to produce oxygen, it didn't escape, because first it oxidized all the iron. And that's what the Australians and Brazilians mine, the iron oxide. And then the oxygen made it to the surface. And then, things started to oxidize because oxygen is very active. So the methane, for example, disappeared, and therefore the temperature dropped and rain formed, and we got life forming on Earth. So these are pristine because on the moon, at the moment, there might be water, but we don't know that there is for sure. So Kevin Knowles worked on this for roughly 3 months, and we solved these 5-fold phases. And they are weird, 2 to 9, not 100 or a simple face. So why should a self-respecting crystal have weird faces? And he solved the faces to be 2 to 9 intersecting with 001, which gives us the 5 sides. And then I used the image in my book, and we also published a paper on this. And when I talked about this to other people, I said, this will never be cited, because this doesn't change the world as we know it at all. It's very interesting, but it doesn't change the world as we know it. But there is one citation, and this is some work done in Technion in Israel. And I didn't know the authors. I emailed them and said, what are you doing? And can you give me all your information so that I can talk about it? Because I like talking. So what they're doing is they're trying to produce strange faces on platinum crystals, because on the chance that the catalytic activity of those faces will be different from the normal crystal. So they use this device to produce strange faces. And they were extremely happy for me to have all the information and to use it to talk to everybody. Now, you all know about additive manufacturing, right? You've been doing it since you were children, all right? You have these Lego devices, and you build them up layer by layer, and the final object is beautiful to look at. And it has intricate structure inside. That's exactly additive manufacturing. So I want to first show you additive destruction. All right, so many of you will have these glass blocks with images inside. And how they are created is exactly the opposite of additive manufacturing, that you focus a laser and you cause some damage inside the glass. So I'm going to show you Tinkerbell being made in this way. So there's a laser going and creating damage to create the Tinkerbell image inside this block of glass. It's absolutely remarkable to look at. Soon there will be wings. Yeah, so these are her wings. Now, this is exactly the process that you use for additive manufacturing, except slightly different, that you have a laser and you feed in powder and you melt layer by layer and you build an object which you cannot manufacture in any other way because it has intricacy embedded in it. And you use powders or wires or whatever. And in real life, this is actually a device being made by additive manufacturing. So you've got the laser impinging on powder particles to fuse them and create a three-dimensional image. So there are loads of these machines everywhere, but to do it in metals is really nice. Plastic, of course, you can buy a machine for your home and use it. This movie goes on, so I will move on. So there are limitations to additive manufacturing. It's an expensive process because it's slow. The productivity is not very high. You are depositing 2 kilograms per hour or 5 kilograms per hour using arc welding. You know, the finished product is not actually the finished product because you have to ensure that all the other surfaces, etc., the channels, fulfill your requirements. And the scales of the products that you can produce are also limited. Nevertheless, there are certain things that you cannot ever make without additive manufacturing. And that's where its strength lies. So just to show you another set of problems, this is by depositing layers. And you can see here that this plate, which was originally flat, is no longer flat because you've got liquid contracting, etc. So you will have large residual stresses in there. Whether that matters or not, I don't know. The surface here is also not smooth. So you will have to do some other operations afterwards. But this is an example which cannot be done without additive manufacturing, and it saves 70% steel. So this is a tool used in industry, and you make it by machining. And this is the corresponding tool doing the same function, okay, exactly the same function, but you can now design it differently, and it has 70% less steel. You could not actually make this by machining. Now, this is a movie that I took in Moscow when I was on the 60th floor of a building, and there was really bad weather, very strong winds and a lot of rain. And I put my mobile phone on the dining table, and I saw the chandelier shaking. So this happens because, if you take a plastic ruler, which is long, then you can easily deflect it elastically, right? So if you make a long piece of steel, like in a tall building, then elastic deformation accumulates, and it can get completely intolerable. This is a building in Taiwan. It's called the Taipei 101, which has 101 floors. And I was very lucky that I could visit it while it was under construction because some of my former students were involved in the construction. So it's 101 stories long. And if something wasn't done, you would get approximately a meter deflection at the top, which would be totally unacceptable from a comfort point of view. So these are pictures which I took when I visited. And this is the largest additively manufactured object in the world. Weighs 600 tons. Very, very clever. Okay, it's not laser deposition. You cut out discs, rather like Lego. You stack them and you make a simple weld here because it's not supporting a load. It's going to be supported by wires. Now, why would you do this in the center of the building? Well, it's a tuned temper. That's right. So it's connected to dampers here. You can see here. And the frequency, etc., is controlled to cope. And even in an earthquake, and there was an earthquake there, it performed really well. Now, the Taiwanese are very clever. So they painted it gold. And this was a couple of years ago when I went back. It's a tourist attraction, a major tourist attraction, because it's a wonderful story, right? The largest additively manufactured object in the world. Now, I'm going to show you things which we have tried very hard and not succeeded, because, you mustn't go away with the impression. I'm going to show you two examples. So this is the hexagonal form of iron, and we can make it on Earth by alloying. We can make it under ambient pressure by alloying. In order to get a transformation from the austenite to the hexagonal iron, it would have to happen at temperatures below 200 degrees centigrade. The only way you can get that to happen is by deforming the atoms in a choreographed manner like ballet dancers. So they all move together. In other words, like martensite, all right? So this is the structure. And no one in the whole world has produced hexagonal iron without this mechanism. So there is no possibility of atoms diffusing any distance at 200 degrees centigrade in iron. So we cannot actually make structures which look like this, which are coarse and crystals of equal size, roughly. No one has ever produced hexagonal iron by a mechanism which requires diffusion. Of course, in the center of the Earth, the story is different. You've got 10 to the 23 kilograms of hexagonal iron in the middle because the pressure there is incredible. And the second thing which I've struggled with enormously is a substance called tetrataenite, all right, which forms in meteorites. And meteorites, cool at 1 degree, 1 Kelvin. Well, it doesn't matter if you use Fahrenheit or centigrade or Kelvin, in a million years. Very, very slow cooling rate, right? So you can actually get diffusion at low temperatures because this particular product, tetrataenite, can only form below 300 degrees centigrade because it's an ordered arrangement of iron and nickel atoms. And the interesting thing about this is that we talked earlier about rare earth metals. Now, this would make a really good permanent magnet. But at the moment, you can only get it from meteorites. So can we make this on Earth? And many people are trying to make it on Earth using creating it from solutions, for example. All right? But nothing is working at the moment. So, 1 atomic jump in 10 to the 4 years at 300 degrees centigrade. So again, I know universities work in the long term, but this is too long. But we can actually do calculations and enjoy the moment. So for the way in which we do calculations is, I'm not going to use the word thermodynamics, but we are plotting energy here and a reaction path. And this is the iron and nickel atoms. And we want to go to the ordered iron nickel tetrataenite. And there's a difference in energy. This is the more stable form, but there's a huge barrier here. It's like, climbing over the Rockies to get to the next sea level side. And that barrier makes it impossible to make it by casting, for example. But it is the favored phase. So eventually, we should try to make it by clever techniques. And one idea which I would like somebody to try, and I don't have the facilities, is to make the iron nickel, disordered iron nickel compound solution in the glassy state. Because if you anneal the glassy state at a low temperature, it will reorder easily. So I need somebody to make this iron 50, nickel 50 solution in the glassy state. So we can get metallic glass, all right? But this would be difficult to cool sufficiently rapidly, but look, nothing in life is easy. So in the meantime, we did first principles calculations to show that if we can introduce hydrogen, and anything you add to this must be at a low temperature, right? Because it disorders about 300. And hydrogen is a small atom which can diffuse very rapidly. All right, so you might ask, well, how can we hold hydrogen in a cylinder? Well, it's molecular hydrogen, it's not atomic hydrogen. So if we can add hydrogen to this, then we would have an even better permanent magnet. So, we have to do something in the meantime, and we did these calculations to show that. Iron is almost never used in its pure state. We add many things to it. We have the entire periodic table at our disposal. And of course, we can get many different phase transformations, hundreds and hundreds of phase transformations by different mechanisms, either by stress, magnetic field, and so forth and so on. So it is incredibly complicated. And I haven't put all the complexity over there in terms of the properties. There is nobody in the world who can predict any of these properties if I gave them the complete set of parameters for a particular steel. Okay, whatever parameters they want, I can provide. Nobody can predict any of these properties in the whole world. We measure them because we need that for engineering design, but nobody can ever predict this. So how do we do this? So there's a huge amount of data around because, before you use it, you have to actually measure the data so that the engineers can say, okay, this will work. Machine learning and the so-called artificial intelligence, the intelligence isn't there, but it's added there to make it sound sexy, has been around for a very long time. And back in 1995, I was working with another professor called David Mackay. He wasn't a professor at the time, younger than me. He taught me everything about this. Science, if you have a difficult problem, you reduce it until you can solve it, right? That destroys the technological goal. So there's a different approach where you use modeling as a tool, which is not sufficiently sophisticated to solve the problem, but it gets you there faster. And you do everything, and then this is very important. How uncertain are your predictions? Because we are predicting things which don't exist with completely empirical models. So, the so-called artificial intelligence is a very simple equation with billions of coefficients. It's rather like the regression lines that we used to fit with just 2 coefficients. But there are billions of coefficients, none of which have any physical justification. And we've written a book about the different kinds of techniques that you can use, but none of them are sophisticated enough to completely solve the problem. So one of the issues is that we have a large number of variables, right? So if I plot the points here on an XY scale, they look pretty random, right? Yeah, I wouldn't fit a straight line through there. So the reason why it looks messy is because some of the variables have been ignored. And if I show you what happens when I include the z-axis, you will immediately recognize what this is. Yeah, so ignoring variables is not a good idea. Trust me, this is the only equation you need for any of this artificial intelligence, right? But it can be made as complicated, or it can have as many terms as you like in the i's and j's, right? And the w's are all the coefficients. And using just 4 of these hyperbolic tangents, I can show you how flexible the function becomes. You can make this surface sing and dance, so you can make it fit anything. And this is not as complicated as what you can do now with billions of coefficients. Now, the problem is that you can make it pass through every point, even though the points are noisy. But we can deal with that. We can identify the noise. So let me ask this young man a question. So I've got a series of numbers there, 2, 4, 6, and 8. What do you think the next one is? Brilliant, absolutely brilliant. So the next 2 numbers would be 10 and 12. But look, I have here this equation in which if I plug 2, I will get exactly 4. If I plug 4, I will get exactly 6. If I plug 8, I will get 6, I will get exactly 8. But when I plug 8, I will get 8.91 and 7.14. So we have 2 models which exactly describe the data, 2, 4, 6, and 8, but which behave differently in extrapolation. And that's the problem of machine learning, that we don't actually know which model should physically work, all right? So I'm illustrating this simply with these 2 different plots. And here where we don't have data, the models represent the data rather well, but not in regions where there aren't data. So this is another kind of uncertainty. It's called a modeling uncertainty, which you have to be wary of. And David Mackay created the Bayesian method for giving us these error bars. So I'm going to show you quickly an amazing result, all right? So this is the fatigue of steels, and most steels break by fatigue. 95% of all failures are due to fatigue. Like this is I took at Colorado School of Mines, where they have a large range of samples. And I created a machine learning model, including these variables, because I have a lot of data on steels, right? Huge quantities of data, measured data. And the axis here simply represents the significance of each variable in explaining the fatigue life. When we plug in steels without any information about them in the original database, we get good agreement in the crack growth rate as a function of the stress intensity range. But I'm going to show you something really crazy. So this is entirely a model based on steels, no other metal. But I'm going to show you that it works extremely well for nickel, aluminum, and titanium. And the reason I'll go back here is that none of the inputs actually say that they are specifically about steels. These parameters apply to fatigue in anything. And therefore, we thought that the model should work for anything. And here you are, nickel alloys and titanium and aluminum alloys. Quite remarkable that you can estimate for things which were not in the database if you design your model carefully. I'm going to end with a feel-good factor that around Indonesia, you know, there's huge damage in the coral seabeds. Indonesia has the largest area of coral reefs, and they used to do dynamite fishing and mining of the coral. So you can see huge damage here. So what do? Well, steel comes into play. So steel has a density which would keep it on the surface of the seabed, even if there is a storm. So you make a device of this shape here, and you attach to it live coral, you can see here. And you just place it on this ocean bed. And a few years later, this actually is what happens, okay? So can you see here the remnants of the original? And if you can't, there's another slide I have. Huge areas of the coral have been recovered. Beautiful, simple technology. The steel is the cheapest steel you can buy, okay, rebar, bent into the right shape. Haiming kindly pointed out that there's a lot of information on my website, including all these books that you can download freely. So feel free to use them. So there's absolutely nothing in the Silicon Valley that could be made without the existence of iron. Absolutely nothing, okay, including your mobile phones, medicines, nothing. And you wouldn't believe this, but the number of innovations in steel is really quite remarkable. And tomorrow I will give a technical lecture. I have a few examples, but I have many, many more to show the level of development in steel metallurgy.